Welcome to The Explainer. Today, we're cracking the code on one of the most sought-after certifications in the entire tech world, the Big Data Analysis Engineer exam. So if you've ever tried to register for the Big Data Analysis Engineer exam in South Korea, you've probably seen a screen exactly like this. The demand is just so intense, it's like a digital gold rush. The servers can't even keep up.
Okay, so here's our plan to demystify the whole thing. We'll start with the data gold rush itself, then walk through your analysis roadmap. After that, we'll get into taming wild data, check out the analyst toolkit, and wrap up with the new rules of data this all represents.
All right, first things first. What even is the Big Data Analysis Engineer certification? And why is everyone and their brother scrambling to get it?
Well, you can think of it as the official, government-backed stamp of approval for your data skills. It basically certifies that you can take a messy, massive data set and, turn it into clear answers that a business can actually use.
Okay, so the written exam is broken down into 4 key subjects. And these aren't just random academic topics, not at all. They're actually designed to mirror the real-world workflow of a data analysis project from start to finish.
So the whole journey starts with planning, right? You got to define the problem first. Then you jump into exploration. That's where you get your hands dirty with the data. Next up is modeling, where you build your predictive algorithms. And finally, it all wraps up with interpretation, where you figure out if your model is any good and explain what it all means.
And this whole process isn't just made up, it's grounded in really well-established frameworks like KDD. That stands for Knowledge Discovery and Databases. It's basically a structured map that guides you all the way from selecting raw data to cleaning it up, finding those hidden patterns, and finally evaluating what you've actually discovered.
Now here's a really crucial tip from people who've actually taken this thing. The exam gets way tougher starting with Subject 2. We're talking about a statistics section that feels like an entire university course crammed into one test. That's why the smartest way to study is to tackle Subjects 2, 3, and 4 all together, because the concepts are just so deeply interconnected.
Okay, so let's dive right into that second subject. It's all about taming the wild, messy data you'll get in the real world. This is data exploration and pre-processing, and trust me, it is absolutely crucial.
You see, before you can even think about building a model, you have to clean your data. And a huge part of that is dealing with missing values. But here's the thing, they're not all the same. Sometimes data is missing just completely at random, like a simple typo. But other times, it's missing for a specific reason, like when people with lower incomes are less likely to answer a question about their salary. You really have to understand the why behind the missing data to know how to handle it properly.
Another beast you've got to tame is the outlier. Those extreme data points that just don't seem to fit in with everything else. And your best weapon for spotting them? It's the box plot. It's a fantastic tool that visually maps out the spread of your data, instantly flagging any values that fall way, way outside the normal range.
But here's the catch, and this is a really important one. An outlier isn't automatically an error you should delete. Think about it. A person weighing 300 kilograms is definitely an outlier in any data set. But a person like that could exist. If you just delete that data point, you might be throwing away a valuable, even if it's rare, piece of information. It really takes careful judgment.
Then you run into this really strange paradox called the curse of dimensionality. Now, you'd think that adding more variables, more dimensions to your data is always a good thing, right? More information is better. But it turns out that's completely wrong. As you add more and more dimensions, the data points actually spread out, becoming really sparse. This makes it much harder for your algorithms to find patterns, and it can surprisingly weaken your model's performance.
And that is why we so often need to reduce the dimensions. We use clever techniques like principal component analysis, or PCA for short. It intelligently combines related variables into fewer, but more powerful, new ones. This not only helps us beat the curse, but it also speeds up our calculations and ultimately leads to much better, more robust models.
All right, so once your data is all clean and prepped, it's time to open up the Analyst Toolkit. This brings us to the core of the exam's third subject, modeling, where we finally get to choose the right analytical model for the job. So the first big choice you have to make is between supervised and unsupervised learning. Think of it like this. With supervised learning, your data has a known target or an answer key.
You're training the model to predict that specific answer. But with unsupervised learning, there is no answer key. You're basically just asking the model to dive into the data and find any hidden patterns or natural groups on its own.
Now let's say your goal is to predict a specific number, like the price of a house or next quarter's sales figures. For that, regression analysis is your go-to supervised technique. It works by figuring out the mathematical relationship between all your input variables and that one continuous value you're trying to predict.
But okay, how do you know if your regression model is actually any good? You don't just guess. You use a powerful statistical tool called an ANOVA table. It calculates things like an F-statistic and, more importantly, a p-value. This tells you if the patterns your model found are real or if they just happened by random chance. A really tiny p-value, that's what you're looking for. It means your model has found something statistically significant.
But what if you aren't predicting a number? Well, if you need to sort data into known categories, like spam versus not spam, you'll use a technique called classification. And if you want to discover brand new, hidden groups that you didn't even know existed, like different types of customer behaviors, then you'll turn to an unsupervised technique called clustering.
Okay, moving into our final section. All of these tools, all of these techniques, they all point to something bigger. A fundamental shift in how we think about data. And this new mindset is really at the heart of this entire exam.
This, right here, might be the single most important idea in the whole curriculum. You see, for centuries, science has been obsessed with proving causation, proving why something happens. But in the age of big data, we're realizing there is immense, incredible value in simply knowing what things happen together. In other words, understanding correlation is becoming just as important, if not more so, than proving causation.
And that's what makes a tool like a correlation matrix so incredibly powerful. It lets us see, at a glance, how different variables move in relation to each other. We can find these really valuable predictive relationships, just knowing that when A goes up, B is also likely to go up, without getting bogged down for years trying to definitively prove that A causes B.
So let's do a quick recap of what we've covered. We've broken down the structure of the Big Data Analysis Engineer exam, we've dug into the really critical challenges of data pre-processing, and we've toured the core modeling techniques that are in every analyst's toolkit. This massive shift from always needing to prove why to just needing to know what, it unlocks a whole new universe of possibilities. You no longer need a perfect, preformed hypothesis to start creating value from data. So the real question this exam leaves us with is this. If just knowing what's correlated is enough to create value, what new questions can you now ask with all the data that's all around us?